Good morning, ladies and gentlemen, and welcome to the Daly lecture. VGP has had some problems in the past presenting the awards to the recipients, particularly the Bowen Award and also the Hayashi Kuno Award at the VGP annual reception. Thus, we are going to try a new practice starting with this AGU. The Bowen Awards and placards will be given at the Bowen lecture, and at the Daly lecture, we will give the Daly recipient his/her placard. In addition, we will announce the Kuno awardees, and they will receive their placards. So we'll start the session by me, first off, introducing Matthew Steele McInnes, the 2017 Hisashi Kuno awardee. Matthew, please welcome. Presenting the citation will be Bob Bodnar.
Thank you, Bill. It's a pleasure and honor to introduce Matt Steele McInnes, 2017 recipient of the Hisashi Kuno Award. It's appropriate for Matt to be recognized by the VGP section of AGU as he has made significant contributions in volcanology, geochemistry, and petrology, as well as other areas of the earth sciences. His research defines and quantifies fundamental chemical and physical processes and provides a sound basis for interpreting field and laboratory-based observations in a broad range of geologic environments. Matt earned his BS with honors in earth sciences with a minor in math from Memorial University, Newfoundland, where he received numerous honors, including the University Medal for Academic Excellence in Geoscience. At Virginia Tech, Matt was named an Institute for Critical Technology and Applied Science postdoctoral fellow, and upon completion of his PhD was honored with the Virginia Tech College of Science 2013 Outstanding Doctoral Student Award. During his tenure at Virginia Tech, Matt investigated a broad range of critical issues in the earth sciences and conducted experimental studies to determine phase behavior of iron-bearing hydrothermal fluids, developed thermodynamically based methods to interpret volatile contents obtained from melt inclusion analyses, conducted theoretical studies to predict speciation and structural states of ions in solution, and developed various numerical methods to interpret fluid chemistry based on laser ablation ICP-MS and microthermometric analysis of fluid inclusions. Matt's PhD research, as well as collaborative research with other students and faculty at Virginia Tech and elsewhere, resulted in over 20 publications in top international journals. Following his PhD studies at Virginia Tech, Matt was offered a tenure-track faculty position at the University of Arizona, which he accepted before leaving Virginia Tech. But before beginning his position at the University of Arizona, he took a 2-year sabbatical to accept the prestigious Marie Curie postdoctoral fellowship where he conducted research at ETH in Zurich. In 2015, Matt joined the Department of Geosciences at the University of Arizona as a tenure-track assistant professor, but just this year, in August of 2017, Matt and his partner Pilar Lecumberri Sanchez were lured away by the University of Alberta, where they both hold tenure-track faculty positions. Matt, congratulations.
So thank you, Bob. Thank you very much. I want to thank some other people. I want to thank my nominators, the VGP section, and the Kuno Award Committee for bestowing this honor. I also want to thank people who have guided me along my career path so far. John Hanchar at Memorial University, was my undergraduate mentor. He was instrumental in guiding me towards graduate school and particularly towards going to work with Bob. I owe much to Bob. Bob introduced me to the world of geologic fluids and fluid inclusions, but he also taught me how to be an effective scientist. And Bob always conveyed an infectious enthusiasm and work ethic that drove me and my fellow students to push harder. I'm indebted to my cohort of fellow grad students at Bob's lab, far too many to name here. And during my PhD, I also spent 1 year as a visitor at GFZ in Potsdam, where Christian Schmidt introduced me to experiments on fluids and melts. I was extremely fortunate to have two, not one but two, exceptional postdoc advisors at ETH in Zurich, Chris Heinrich and Thomas Driesner. Both broadened my perspectives on geologic fluids, both from large-scale processes down to the micro scale. And throughout all this time, several early career colleagues became some regular collaborators and friends who've helped me branch out into different fields, especially Georg Spiekermann, Joachim Reimer, Kyle Ashley, and Rosario Esposito. And of course, another regular and long-term collaborator of mine also happens to be my wife, Pilar Leckenberry Sanchez, and I cannot express how grateful I am to Pilar for all of her support. It helps that we can discuss science both at work and at home without arguing too much. Thanks.
VGP is very, very lucky and unlucky at the same time. This year, it was a challenge. We ended up with two equal but different Kuno recipients. It is a very healthy expression of where we are today. And with that, I welcome James Watkins as the 2017 Hisashi Kuno Award recipient. Michael Manga will be the citationist for James.
Bill, it's not about luck or unluck. It's all about really hard work. James Watkins embodies the essence of modern petrology and geochemistry, continuing the Kuno legacy of quantitative study of igneous rocks. Jim has developed new understanding of diffusion-related isotopic effects in magmas and aqueous fluids. He did so by combining novel high-temperature experiments, careful isotopic analysis, modeling, and non-equilibrium thermodynamics. He's also been inspired by natural rocks. He developed a new approach to extract the pressure history of magma from the glass around bubbles. He's derived and tested with experiment a nearly complete description of non-equilibrium isotopic effects in the formation of calcite from aqueous solution. These results put measured fractionations on a firm theoretical basis and promises to make calcite an even richer recorder of past Earth's surface conditions. Jim exhibits no fear in learning new techniques in theory and bravely tackles daunting problems even when he has little previous experience. But at the same time, he remains a patient and understanding collaborator, always willing to pool expertise to address difficult problems. And it is this combination of that makes him both a good friend and an academic and intellectual role model. In recognition of original research on fundamental aspects of magma transport and aqueous mineral growth, we're pleased to present James Watkins one of the 2017 Kuno Awards.
The most uplifting surprise about this award was learning that someone that I deeply admire but haven't worked with was responsible for my nomination. So my sincere gratitude to Cinti Lee, whose science, art, creativity, and kindness are a big inspiration to me. Don DiPaolo and Rick Ryerson were my other letter writers, and I don't have time today to do justice here, but I trust they know how much I appreciate everything that they have done for me and continue to do for me. I am a product of public education. My hometown has 2,000 inhabitants, and I attended a very affordable university. And despite my lack of pedigree, both Don DiPaolo and Michael Manga took a chance on me, and for that I am forever grateful. It was a tremendous privilege to learn from them and to observe their scientific leadership firsthand. I owe this award and share it with my co-authors and collaborators, in particular Chris Huber, Jim Gardner, Feng-Zhen Tang, Casey Sanger, Laurent Devrion, Kenny Beefus, Eli Block, Paul Wallace, Ilya Bindeman, Mark Reed, among others. It is a pleasure working with all of you alongside of our students. Thanks also to Sonia Esperanza and Jen Wade at NSF for their leadership in supporting early career scientists such as myself. And lastly, I thank my wife, Amanda Thomas, who is not only a brilliant seismologist, but an amazing wife and now mother of 10 months. Thanks again.
Again, congratulations, James and Matthew. So, I thank Catherine Chauvel for actually accommodating this period of time for the presentations of these awards. Now I'd like to ask Catherine to come up and to give us the 2017 Reginald Daly Lecture, A Geochemical View on the Interplay Between the Earth's Mantle and Crust. Catherine Chauvel.
Okay, hello everybody, and I really would like to thank Bill for asking me to give this lecture, and I hope I'll be able to give a talk that interests the entire VGP community and not just the geochemists. Before I start, I just want to say that I'm going to show things on the laser on the what is it? For you it's a right screen, for me it's a left screen. So, because it's too complicated to go on both sides, so if some people want to move from that side of the room to the other, you're welcome to do it. So, I'm going to today talk about the geochemical approach to look at how the Earth's mantle and the Earth's crust interact. This presentation is not just due to the work I've done myself, but of course it involves a lot of other people, and I like to recognize, you know, how much they contributed. The first one is my colleague Eric Levin, who you see here on the side, and then 4 students: Marion Carpentier, Chazal Labanier, Marion Garçon, and Hélène Delavaux. Some of you might notice they are all female. It might mean something. So let's start. Mantle and crust. So, how did it go? At the beginning of the Earth's history, shown here with the picture on the Hadean, there was basically no crust to start with. The Earth consisted of a core and a primitive mantle that we also call bulk silicate Earth. As time went past, we reached the situation that's present today, here, shown here, where about 40% of the Earth's surface is continental crust. So this material that formed the crust, the primitive mantle here, produced the continental crust and left behind a depleted mantle reservoir. So the major question from a large picture point of view are when and how continental crust formed. And so once it's formed, how is it destroyed and how much of it goes back into the mantle. and what impact it can have on the composition of the mantle. So this is the thing that I'd like to talk about today. So we're going to do a journey. We're going to start from how mantle and crust, shown here, are differentiated. And then at the surface, we will see what happened during the sedimentary cycle, how weathering and erosion can change the way the chemical elements behave, where they go, and how they can be fractionated. Then these sedimentary piles end up in the sea, in a subduction zone, to be recycled in the deep earth. Part of it goes into the arc, and the rest goes into the mantle. So this is a journey we're going to do during the talk. So the present situation for continental crust is shown here. Just a number of figures, because I think it's quite important. As I said before, 40% of the Earth's surface is continental crust. The rest is oceanic crust. And 30% of the continental crust is underwater. So it's a large surface, and it's shown here on this figure that I took from Roberta Rodnick article in the Treatise of Geochemistry. It is a thin layer, only 40 kilometers, and you cannot see it on the, that scale. And it is thin, and it represents only 0.5% of the mass of the planet. So it's minuscule. So why is it important? It's very important in geochemistry because most trace elements are present in the continental crust. And you see here a trace element pattern with all sorts of elements organized here by order of incompatibility. And the concentration from Roberta's evaluation of total continental crust shown. So the concentration of the element on the continental crust normalized to what it was in the primitive mantle. So we see that it can be very enriched for the elements that are the most on the left, up to 100 times the mantle, and less enriched in the right side of the diagram, where it reaches something like 5 times. So there is a fractionation of elements, with some more enriched than others. So we can also look at it in a different way, and here I showed the percentage for each element of the percentage of the element that is in the continental crust relative to what it was to start with. So we see that for some elements, the most incompatible elements here, including some key ones such as thorium and uranium, and lead here, are extremely enriched in the continental crust. You see that basically more than a third of the budget is in the crust and is not in the mantle. So that's a very huge enrichment for something that represents a very small mass of the planet. So making the crust with such enrichment has some impact on the mantle. So here I show on this figure the mass balance calculation that can be made if you start from a primitive mantle source that would be on this figure at 1 all the way along. That was a bulk solid earth to start with. Making this the crust, the present crust, volume and mass, creates depletion in the residual mantle. And I showed here 2 types of trace element pattern. The blue one is what you can calculate if the residual mantle is the whole mantle. So we see that it's not very depleted, but it is depleted in the most incompatible element here. And if the crust is extracted only from the upper mantle, then we have the green pattern here, and you see that it doesn't make much difference for the least incompatible elements here on the right, but it makes an enormous difference for the most incompatible element, and for some of them it's just simply impossible. They got off scale here, and some values are negative. So it's a huge depletion, and it raises question about how is it possible that the upper mantle is the complement of the continental crust as a whole. It seems to be difficult. Al Hoffman gave a talk yesterday and mentioned that type of thing, so I'm not going to come back on it, but he pointed that out very nicely yesterday. So the approach used by the isotope geochemist, and here is a figure that I took out of the excellent book written by Bill White. It's behind the thing here, I can't point it. So it's a figure that comes from Bill White's book. And so it's a bit small, but I'll explain it to you. Here is plotted on the x-axis the concentration of neodymium, an element for which we can measure isotopic composition. So concentration of neodymium in the crust divided by that of the bulk solid earth, the primitive mantle. So there is a range of estimate for the continental crust shown here by this brown field. And on the y-axis, there is the relative mass of the depleted mantle if we want to make a mass balance that suits the isotopic compositions. What we see here is that if the primitive mantle is chondritic, as we thought for a very long time, then we follow this line, and we see that for this range of concentration in the continental crust, it implies that about 25% plus minus 10% is, of the mantle is depleted. Okay? Now, in the recent years, because of the measurements that have been done on the 142 neodymium isotopic composition, it's been suggested that the primitive mantle maybe was not chondritic. And it's been suggested that it could have a very high epsilon neodymium value, such as something like 9 here, this line, or maybe a bit lower like this line. And you see that if the Earth was really far away from being chondritic, then it's simply impossible to balance the amount of neodymium that is in the crust towards, relative to what there was to start with, because more than 100% of the complete mantle would have to be depleted to create the crust. So that's a bit of a problem. So now let's move to the timing. Crust has been formed, and I think most of you have seen these curves. This is a very nice drawing that has been given to me by Bruno Duim, who published several papers on the issue. And you see here the time, Hadean, Archean, Proterozoic, and Phanerozoic time. So beginning of Earth, present day. And here are the curves, all sorts of curves, that show the volume of the continental crust at any given time. So we see there are basically a large range, but there is basically two extreme models such as the Armstrong model here, shown with the A, where it's suggested that basically the entire volume that exists today was created very early in Earth's history, and then recycling just processed what was at the surface, and any addition was compensated by destruction. That's one end member. The other end member is this type of model at the bottom, where most crust, the volume of crust was very small at the beginning of the Earth's history and increased drastically very recently. And you see there are all sorts of curves in between, so there is all sorts of models. There is no real big agreement on that. And Bruno Duim has his favorite curve, but I don't have time to show all of that today. But the other point I want to make here is that this is a bit confusing for most people, and it was including for myself for a while, which is that the volume of continental crust that's plotted here doesn't mean is the volume as a given instant, and this crust can be destroyed to be replaced by another crust, which means that in the end there is no way using this curve to know the average age of what is at the surface today. Intuitively, I would have thought that when you have a curve like the Armstrong curve, you must have had 100% of the crust that's old. So it should be an old crust, but no. It can be destroyed and replaced by a younger one. So it's a complex relationship between the volume, the percentage of the volume, and the average age of the crust today. So how do we calculate or estimate continental crust modelage? Because this is something that's not very well known. This is a schematic thing where I have time on the x-axis, with today here and the beginning of the Earth's history here. And here is the growth of the neodymium isotopic ratio through time. The green curve shows the evolution through time of the bulk solid Earth if it's chondritic, and the blue line shows the evolution through time of a depleted mantle, simplified model, and the mid-ocean ridge basalt would plot up there. What we can measure today is a range of value of individual crustal terrains, shown by this orange box. And we can measure the samarium-neodymium ratio of these individual crustal segments, and we can calculate back the average age of that crustal segment. This is shown by these orange lines here. And depending on whether you want to take as a reference a chondritic reservoir or you want to take as a reference a depleted mantle, you get different model ages. Okay? So if you have a range of terrain like that, you can get a very large range of ages, you see? It can go from extremely old to quite recent. So the question is, where is the average? And what is the average age of the crust? How can we determine that? Just, I wrote that on the side just to remind some people who don't really realize that always, but these model ages are not real ages. It's an average age. So I use an approach to study first the upper continental crust and to try to determine its average composition and its average age, its model age. So what we did is we worked on a large number of LEUs, a lot of data points you don't see behind this star, it's about 50 or 60. And we measured trace elements and neodymium isotope and hafnium isotopes. They are incredibly uniform values, you see here. And we can calculate an average for neodymium, -10 epsilon plus -1, so it's a very small range. And in hafnium, a small range as well, since it's only ±2. So what is important is that the LEUs come from several areas in the world, so it averages the surface material of a very large, large continental areas. All of them are the same behind the star, except for these three Argentinian samples here, which happen to be full of recent volcanic rocks, so they're not very representative. And the third important point is that these LEUs samples are incredibly uniform compared to individual measurements done mainly by my friend Jeff Fervort. All these brown points here that spread from here all the way down to here. Okay, so it's much more uniform because the sedimentary process did the mixing for us. Okay, so we can take advantage of that. So I'm quite convinced that it provides a good average for large continental area present at the surface. So using the same data, we can estimate, so here we have the neodymium isotopic composition I just showed you before, and we measured the samarium-neodymium ratio, so we get this star, this is the average composition. So we can provide a samarium-neodymium ratio for average upper continental crust, and using this samarium-neodymium ratio and the isotopic composition, we can calculate a model age, and we get a model age of 1.8 gigayear. This average model age is in fact very similar to a value that had been suggested by my friend Steve Goldstein a long time ago. We haven't changed the value very much, in fact. But more interestingly, we can use that to try to get some constraint on the lutetium-hafnium ratio of upper continental crust, a value that's extremely poorly defined. So what we did is we used the relationship between neodymium isotope and hafnium isotopes and using the data shown here. And since we know the model age of the given by neodymium, we can assume that the model age given by hafnium has to be identical. And so we can calculate the lutetium-hafnium ratio. And this is what is shown in this figure here, where we plot the neodymium model age versus hafnium model age, and calculate how it changes the hafnium model ages depending on the lutetium-hafnium ratio that we use, because the lutetium-hafnium ratio is very highly controlled by the amount of zircon present in the rock, so it can be very variable. So if we want to have similar age for hafnium and neodymium and fall on this line, it constrains the lutetium-hafnium ratio, and we obtain this value for upper continental crust. So why is it important? And I give you an example here because I think it's quite important. I used here the data set compiled by Ken Condy. There's about 4,000 detrital zircons, and he used, this is a plot that he's done, and you see that if you plot the epsilon hafnium value of all sorts of detrital zircons as a function of the age, you get this big cloud. And for an individual point, I'll take one here, depending on the lutetium-hafnium ratio that you use to calculate the model age, you're going to go follow the green line there, or you're going to follow the brown line here. And the ages are very different. Okay? So the oldest it is, the larger the difference is. Here you probably don't see it's too small, but there is not much difference for that point chosen here. So then you can calculate the histogram of all these ages, and I'll show you here the difference between the curve calculated using my favorite lutetium-hafnium ratio, and the green one shows the histogram that you get for model ages if you use the value that the Ken Condy had. And there is a significant difference, and it can be up to 500 million years. So it's an important difference, and this is a lot of calculations are very sensitive to that ratio. Okay, so now how can we calculate the model age for total crust? I go back to my time versus neodymium isotopic composition. Here is a depleted mantle, and I showed you that we determine an average value for the upper continental crust. We determine a samarium neodymium value for the upper continental crust, and we have a model age of 1.8. Okay? So what about the rest? The rest, we don't really know what it is. It's not very well constrained. So what I do here is I take extreme examples. Here, if I take a very old age for the lower and the middle crust, here taken as Hadean, and I use the samarium neodymium ratio provided by Roberta, I can calculate the present day value of lower plus middle crust. Then I can mix up this composition with the composition of lower and middle crust using the proportion provided by Roberta, use the samarium neodymium ratio of the total crust, go back and get a model age for the total crust. So you'll see here that the model age of total crust will vary significantly depending on how old the lower and the middle crust are. So this is actually something that I summarize in this figure, which looks a little strange because it's a model age on the x-axis and a model age on the y-axis. So it looks a little strange. But what I've done is, if we impose various ages for the lower and middle crust model ages, so here very old, down to 1 billion year for the lower plus middle crust, we have the model age of upper crust, which is always 1.8. Then we can calculate the total crust model age. And we follow this curve. Okay? So if the lower middle crust are old, the total crust will be old, and you can go up to 3 billion years. And if the lower middle crust are younger, then the total crust will be younger. In the case where lower crust and middle crust are younger than the upper crust, then the total crust will have a very young age. Okay? So that's about how far we can go now, and I think we need good isotopic constraint on the lower and the middle crust so that we know where we are on that curve and we can calculate the total crust. This remains to be done for the future. Okay, so now we're going to start moving on what happens when the crust is created and is destroyed by sedimentary processes. So here's a sketch of what happens on continents after the rocks arrive at the surface. They're subject to weathering processes and erosion, and rocks and elements are transported by rivers to end up usually either on the plains or in the ocean to be deposited. The soluble elements are mainly transported by the water in the rivers, and the insoluble elements are mainly transported as mineral phases, and they travel far or not far. In addition, particularly in the oceanic environment, new phases are created by biogenic and autogenic processes, so that's independent of magmatic processes. So here is what happens in the river. This is a figure that looks a bit crowded, but I took it from the nice article of Jérôme Gaillardet in the Treaty of Geochemistry. And what he shows here is the proportion, it's a log scale here. So it's a proportion of all sorts of elements listed at the bottom here, how they are enriched in river waters relative to a reference that's said to be sodium. We see that most trace elements are not very soluble, and they are not enriched, they are kind of depleted in the waters. But I think it's still important, and I highlighted some elements that are the ones that are useful for all the radiogenic isotopes. So there is uranium here, with lead and thorium down there. There is rubidium here, with strontium up there, and then the rares are here, and hafnium is down there. So we see that some parent-daughter ratio can be modified because one element will go in the water and the daughter element will not go in the water, such as, for example, uranium, that's much more soluble than lead or thorium. But in terms of quantity, it's not very much. So what is important is to look at the sedimentary load, the solid phase. So I'm going to concentrate on the solid phase, and I'm jumping directly to one pair of elements, the thorium and uranium, and looking at beautiful work that's been done by my previous students, Marion Carpentier, and she did that when she was in postdoc in Vancouver with Dominique Weiss. So we did this project together, and she studied sediments offshore the continent, and here is a compilation of all sorts of data that has been published and data that she acquired. And you can see two colors. There is some kind of brownish colors and some bluish colors. And she measured thorium, she measured uranium, among other elements. And what we see is that when the crust that's eroded is young, quite recent, then the thorium-uranium ratio shown here, it's behind the black thing, I can't see it, but here is a number of measurements done for a certain value of thorium-uranium at the bottom. So what is blue here corresponds to young crust that's eroded to produce sediments in various localities in the world. And we see that the thorium-uranium ratio is low and doesn't spread around very much. When the crust that's eroded here, shown by the brown points, is old, so for example the Amazon area or any old craton of that type, then the sediments deposited offshore have extremely variable thorium-uranium ratio, shown here at the bottom, very low ratio, very high ratio, sorry, and very variable. And the average is much higher than it is in the sediment produced from young crust. So why is it important? It's important because it shows that there is a preferential removal of uranium over time by rivers. It's consistent with the figure I showed you from Gaillardet, where uranium was removed preferentially to thorium. So I think that's important because it has impact on the lead isotopes over time in the continental crust. It's a process that goes only one direction. So now let's move to other type of sediments because I think there's a lot to learn from large river systems here. Here is the Ganges, and this is a work that's been done by my student Marion Garçon. She published several papers, beautiful papers, and so she studied samples of sediments that have been collected down the river, from the Himalaya all the way down to the delta. The Ganges is a very large fluvial sediment system. It carries an enormous amount of sediment every year, and the end result is a big delta that's offshore, the Bengal Fan. It's a very long river system, and it has sources that are very interesting because they come from the Himalaya up there, but they also come from the Deccan Trap and the Indian Shield that have different composition from the Himalaya, or at least the Deccan Trap does. So we can look at what happens when sediments are collected down the river. Is there changes when we go down the river, or does it remain the same? So one aspect that I want to focus on today, among all the data that she obtained, is the fractionation of the two isotopic system, neodymium and hafnium, when you collect samples down the river. Here is the course of the river. So this is the sea, and here is the Himalaya, basically. And you see the data points correspond to the various samples that have been collected in various places. At the top is shown the neodymium isotopic composition. At the bottom is shown the hafnium isotopic composition for the same samples. There are basically two types of samples in the sediments. They are what we call the suspended loads, so it's fine-grained particle type of sediments. And then there are the bed loads, which are basically usually coarser sediments with quartz and heavy minerals. So what happens is that during the transport down the river, minerals are sorted, and some travel further away than others. The heavy mineral remain in the bed load, and they don't go into the suspended load because they're too heavy, as a matter of fact, very simply. And the end result is that it decouples hafnium and zirconium that are shown as this big sharp positive peak here in the bed load banks, when you have no big positive anomaly in the suspended load down there. And it has impact also on the neodymium, on the isotopic composition, because the various minerals had previous history on the continent before. So when we go down the river, you see that the neodymium isotopic composition does not change. It remains constant, but it's not the case of hafnium. And you see that the further we go down the river, the larger the spread gets. The bed load samples are at the bottom, the suspended load samples are at the top. So the two isotopic system gets decoupled during transport. So now we can look at this data by putting them again in epsilon neodymium versus epsilon hafnium space. This is a terrestrial array of Jeff Vervoort. Here are some oceanic sediments, and here are the data that I showed in the previous figure. So here it looks like a relatively small field and neat field, but in fact there is a vertical deviation, and which I show here in this part of the figure, that you can calculate this vertical deviation from the terrestrial array here, and this is called capital big delta hafnium here. And we see that there is a positive trend related to the type of sediments. The fine-grained sediments have high alumina silica ratio. They're mainly clays. And the heavy minerals are in the coarse-grained sediments down at this end, where there is a lot of quartz and zircons. So you create this fractionation, and the finer the particles are, the higher you go in this space. Okay? So that happens on the continent. So what happens when you get to the ocean? We could not measure things offshore the Bengal fan, but here are some other examples. I'm going to give you two. The first example is from the sediments that were collected offshore the Cascadian Arc, work done by Marion Carpentier. And so they're collected here next to Vancouver Island. And so it's a bit crowded, but the major message I want to show here is that there is, again, the same thing as what we see in the Ganges, a vertical deviation. And the vertical deviation from the terrestrial array relates to the type of sediments that are the grain size of the sediment. When the sediments are fine-grained, the deviation is large. When the sediments are coarse-grained and contain a lot of zircon, the deviation does not exist. So we see offshore on the sea the same process that, that is maintained and exacerbed. And here another example, the last one, which is two sites that have been samples from two sites analyzed offshore the South American continent, where a lot of material comes through from the Amazon. And there is this site is relatively close to the continent, this site is far away from the continent. Both of them are in front of the Lesser Antilles Arc. And here we see the same thing again. In the site far away from the continent, the decoupling is large. Here is the terrestrial array, large decoupling. When the sediments are deposited close to the continent, then they are on the mantle array or very little deviation. So it's the same thing. And so the distance to the continent increases the decoupling. So that ends up providing a general picture about the oceanic, the composition in neodymium and hafnium of sediments worldwide, and you see that most of them are above the terrestrial array that's shown here in blue. Okay? They're all above. So they're all above, so what does it do? This is what is subducted in subduction zones. And what I show here is the same figure again, neodymium isotope, hafnium isotopes. Here is the mantle array, which is like the terrestrial array of Jeff Vervoort. Here are the fields corresponding to all the oceanic sediments that have been analyzed in the world. And here, all these dots corresponds to the data that have been obtained on island arcs, volcanics. And I think that it shows clearly that the island arcs defines an array that is different from the terrestrial array, and the reason why it is displaced towards the top is because the average composition of the sediments that make it into the subduction zone is different from the composition of the continental crust from which they come from originally, because the zircons didn't make it. So it's a one-direction process that affects the mantle and the crust over a long period of time. Okay, so what else happens in subduction zones? The questions that I think are important to ask is how much sedimentary material contributes to the arc. So when it gets into the subduction zone, part of it goes into the arc, and the rest goes into the mantle after it passes subduction filter. So I'm just going to show you a few examples. In arcs, geochemically, two enrichment processes are known, and it's been demonstrated a long time ago by Tim Elliott and Terry Planck. And basically, if you take a ratio of trace elements, here is a mobile element over an immobile element, barium over thorium, and at the bottom on the x-axis is the lanthanum-ytterbium ratio, which is a ratio of a highly incompatible over a less incompatible element. You see that all the arcs define a hyperbola here. That can be explained by sediment melting when you move along the x-axis and by fluid transfer of the element when you move along the y-axis. This is a worldwide fixture. You see there are arcs from all over the world here. If I take the example of the Lesser Antilles arc, which is an arc that I like and I know about, we see that it's exactly the same thing. In the Lesser Antilles arc, both processes occur. They are fluid transfer and in other places sediment melting, and a lot in the middle as well. But both processes exist. And this relates to the geography along the arc. So here on the left, you have a map of the Lesser Antilles arcs with the various islands. The South American continent is down at the bottom. And here I plotted a ratio of lanthanum-ytterbium, so the trace element ratio that shows sediment melting as a function of the latitude of the island. So this corresponds to where they are along the arc. And you see, I think, quite clearly that in the south, when you're close to the South American continent, the way elements are transferred from the subducted slab to the arc is sediment melting. And when you go up to the north, this process seems to disappear. On the opposite, if you look at the ratio of a fluid mobile element over a non-fluid mobile element, barium thorium, then we see the exact opposite. The fluid transfer occurs mainly in the north of the arc when you're far away from the continent. So the processes exist both, but not in the same place. So there is a large transfer from fluid here, but something I want to point out is that the source of the fluid is not the sediment. And strontium isotopes are very useful to say that, because you see that all the fluid, here is a strontium-thorium ratio, which is like barium-thorium in a way, and all the fluid-rich arc lavas from the north of the arc are located here. And when you look at the strontium isotopic composition that corresponds to this enrichment, you see it's very low. It looks like mantle. It looks maybe like the subducted basalt, but it does not look like sediment. Sediments would be out there. Okay? So the strontium that's present in the sediments finds its way down and is not transferred by the fluid phase into the arc. It goes down in the mantle. So what are the type of budget can we do for the sediments that enter the subduction zone? With Jeff Ryan, we made some kind of compilation, and we tried to evaluate how much of a large number of elements is sent back into the mantle and goes through the subduction filter without being affected. Some elements never make it, such as boron. Other elements barely make it into the mantle, and some of them are entirely transferred, more or less entirely transferred. And I highlighted here in red the elements that we use, for example, for isotopic ratios. So hafnium is basically sent back, neodymium almost as much, and so on. So there is, again here, some significant fractionation of parent-daughter couples. You see that uranium is sent back to the mantle more efficiently than lead, that I cannot put. It's somewhere here, I think, this one. Okay, so it fractionates the radiogenic pair once again. So what is the impact on the Earth's mantle? Here I show a figure that a very nice paper by Porter and White published in GQ a few years ago, where they made a budget of the a large number of trace elements of the subducted slab. And what is good about what they've done is they took into account the entire residual slab composition. So they estimate what the proportion that came from the sediment, but also the proportion that came from the subducted basalt, which is something that we cannot do when we use the isotopic composition, because the subducted slab has a composition, the subducted basalt has a composition that's similar to the mantle wedge, so we can't differentiate the two. But by using their approach, they could, and what they show basically is that there is a significant amount of enriched material that's sent back into the mantle. You see here the significant enrichment of the most incompatible element, a significant enrichment of lead contents. So what are the long-term effects of on the mantle? I'm getting now to the end. So the long-term effect on the mantle, I couldn't resist showing this figure of my two mentors, Bill White and Hal Hoffman. Their famous paper from 1982, which shows that the crust basalt per sediment is recycled into the mantle. Part of it might be stored there, and this is getting like a fashionable place again today in the last few years. It can be the source of oceanic island, and part of it certainly mixed into the general system and affects the composition of lower and upper mantle. I'm going to give 3 examples of things that that are good signs of recycled material. Here is the isotopic figures. I think it's a little small, but strontium isotope versus neodymium, and so on. And here we have the boxes for the mantle zoo thing. All the isotopic variation known in ocean island basalt and in mid-ocean ridge basalt. And I will focus on 3 places: the EM2 end members, which has high strontium isotopes and continental flavor; the EM1 end member that has a lower strontium isotope, but also a continental flavor from the neodymium perspective; and also on the depleted mantle source of mid-ocean ridge basalt. So I'll start with the depleted mantle, showing a calculation that's been done by my student Marion Garçon. And so it's a little complex, but anyway, what we did is that we used the composition of mid-ocean ridge basalt and ocean island today. We estimated the composition of a recycled material that consists of oceanic basalt recycled in the mantle and oceanic sediment recycled in the mantle. We calculate that. And if you want to, then you can estimate what would be the depleted mantle if there was not this component. How would it be? And we see that it doesn't lie on the terrestrial array. It's displaced to the right. So higher neodymium, but not much higher hafnium. So it has an impact on the slope of the terrestrial array that we see today. It might have rotated. And now quickly, the EM2 continental contribution. This is something I think that everybody agrees on, and I just want to insist on something that Al Hoffman has been showing in his treatise of geochemistry paper, where it's important. I just want to highlight the fact it's important to couple isotopic composition with trace element ratio, and particularly the canonical ratio niobium-uranium, shown here, where we see that in the EM2 type of lavas, there is a strong relationship between the isotopic composition and the trace element ratio that's not supposed to be changed in the mantle. So this is going to continental crust. And here is a compilation I did recently on the Society Island, and we see that for cerium lead, it's exactly the same thing. When strontium isotopes go up, cerium lead goes down towards the continental crust. And now the last example, very nice work done by my latest PhD student, Hélène Delavaux, where she went to Nancy and measured with Émilie Thomasso some sulfur isotopic composition of sulfide inclusion in minerals from lavas from the EM1 end member here. And what she found is what is shown here in red, which is that there is a mass-independent fractionation of the sulfur isotopes in these sulfides in the present-day lavas. How can you explain this mass-independent fractionation? The most likely interpretation is that it's very old, because mass-independent, here is the big delta sulfur 33, shown as a function of time in Earth's history. Anything younger than 2.45 billion years has no anomaly, and anything older has large anomalies. So what we think is that this anomaly were created more than 2.45 billion years ago, and it was at the surface, because this only occurs at the surface. So this probably means that it was a sedimentary origin for the component that is found now in EM1. So, summary, and the question to be addressed for the future generation, at least in my opinion. The continental crust and the mantle have been interacting for a long time. The surface processes modify the composition of material because when it's removed from the continental crust. So we can't just take bulk crust and assume that this is what goes back in the mantle. There is fractionation, and sedimentary processes are very efficient. The subduction factory modifies the composition of the subducted material again, because some elements are transferred via fluid phases and others are not. Therefore, the recycled material is sent back in the mantle, and it's been shown that we can identify it both in the source of Ocean Island and in that of Moore. So here the thing that I think we should address in the future years: what is the average composition and age of the total continental crust? We don't know. And what are the effects of processes other than subduction? I'm thinking here of delamination, which I didn't talk about, and relamination, like Peter Kellerman loves, and I don't know if he's in the room, but these are kind of processes that will have different effect from the subduction processes. Okay, thank you.
Thank you, Catherine, for that excellent discussion. We have some time for questions if people have time to ask them, but we ask that you use the microphone, and CC will deliver that microphone to you if you raise your hand.
Hi, Catherine. Thanks for your talk. Very good summary. Question that I was thinking about when you were showing the hafnium isotope fractionation in fine-grained sediments, presumably due to the zircons going into the heavier fraction, but where is that heavier fraction, and where is the complement to the stuff that's plotting above the terrestrial array? Shouldn't there be something below it then?
No. Yeah, no, I know it's counterintuitive. It's not below. In fact, it stays on the array because of mass balance relationship. And the zircons, if you take the crust source of zircon is going to be on the terrestrial array, the zircons will move away from the terrestrial array when they get old, and then they move towards high neodymium and they keep their hafnium. Okay? And this is actually what happens if you look at some of the Himalayan zircons.
Well, you really summarized, I think, the state of the art extremely well here, but it also left open, I think, what remains the major paradox in all this. There is plenty of evidence, as you pointed out, that there is lots of continental crust being subducted into the mantle, and it's very hard to not see that. Yet, when we look at the mantle rocks, there are a few places where we see this recycled material resurfacing, and we focus, you know, like the, well, I won't say that, but you know, we focus on these. We focus on the EM2s and we focus on the EM1s, which have undeniable signs of recycled continental material. But the fact is that the vast majority of ocean island basalts don't show this signal. And in fact, when you look at oceanic basalts, the recycled material is the exception rather than the rule. Now, if we have subducted over the course of geological history at least one continental volume, that signs of that recycling should be everywhere, and we don't see that. And I think that major paradox remains. You know, I don't know how we're going to solve it with our conventional methods that we have used so far.
Thanks, Al, for the comment. I entirely agree with you. We always look at the extreme and we don't look at the average, and the average is in fact more important. And that's correct that there is hints of real crustal signature in few places, and in most of them there's not much. That's correct. I think what we need to do maybe is we need to be able to quantify when significant amount of crustal material have been started to be recycled, so that we can evaluate quantitatively how much material it is and how it can affect things. And if it's well mixed, then it will change the average as well, and I think we need to quantify that mathematically. I've been trying to do things like that with my colleague Eric Levin, and we were quite happy about the result, and then you came up with your canonical ratio that didn't change. And so that's correct. We can't change it. If you send sediment back into the mantle, it should have a major impact of some of these trace element ratios, and we don't see it. So maybe the early years had a different niobium thorium ratio, for example. I don't know. I think it's worth looking at.
I just disagree a little bit with Al. I think subtly we do see it everywhere, particularly in the non-traditional stable isotopes, or even oxygen isotopes in Hawaii. I mean, you're seeing a subtle crustal signature in that. But what I really wanted to say was to add to Katrine's list here of other processes that we geochemists have systematically overlooked, and that's subduction erosion. And we overlook it because we just can't get a chemical handle on it. Yeah. But that's a really big problem.
Yeah. Yeah. I agree, Bill. So we can go for lunch. It's okay. Finish.
Let's thank Katrine one more time for her lecture.